All right, John Appleby, I'm from Acorn Product Development. I'll preface by saying I'm an engineer, so I like to talk about numbers, spreadsheets, MATLAB, try and skip over some of that that's in here, but we are a company of engineers and really operate kind of on data. Barry was kind of my plant over there, talking about ROI. That's a big part of what we do. We're really approaching this from the product side. We get a lot, hey, this costs too much. This costs too much to make. How can we make it faster? Can we fix that by adding robots, by increasing automation? Can we fix it by changing the design, by moving it to a low-cost region? What's the right approach? And really where we start is really approaching that from data. How do we do that from an analysis standpoint? What's the right ROI model? Again, because robots aren't free, so at least not yet. So. My slides. That's it. All right. So, a couple things on successful products. Good to keep this in mind. Obviously, it has to meet the needs of the customers. People have to want it. It does what it's supposed to, or it does it well enough. It has to be available. People have to be able to buy it, and on the shelf is kind of a figurative term here, so it can be on the computer as well as on the shelf. And then it has to cost the right amount of money. We get approached a lot from clients that say, we want this as cheap as possible. Well, that doesn't really mean anything. It's what's the right price that it makes sense from a business standpoint? What's the right price that makes sense from a product standpoint? Has to be profitable for the business. Also has to be profitable for the supply chain. Has to be valuable to the customer. There's lots of elements to the cost as a just not the kind of bill of materials cost at the bottom of the spreadsheet. And we get a lot. Why can't you make this cheaper? And the big piece of this is in the concept and kind of preliminary design phase, 85% of the cost of the product is essentially locked. When you make that initial architecture decision, when you make that initial layout, construction, material choices, you are really limiting what the overall architecture, what the overall cost of the product can be. Obviously, that's where we like to focus. Obviously, that's where we want to put all of our effort. If we design a whole product and then say, oh, well, we'll have 100 robots at the end to kind of put it all together, really the cost savings may be upstream from that. Also turns out, not shocking, but you really can't make it up in volume. It really doesn't come out of just making more of them. And unfortunately, if you want to blame someone, it's folks like us, and I'll put myself in that category for now. It's really, again, the upstream decisions that you make is really driving this. So I wanted to talk through a little bit of that today. First, a little bit about us. We're a product development firm. Our Cambridge office is kind of out the window that way. Founded by a couple of veterans from Silicon Valley. Ken and Tim both came from Next Computer. Ken was the head of the mechanical engineering group for Steve Jobs. Has some great stories of working for him that don't show up in the movies. But we have about 30 people globally. So office here in Cambridge, office in Silicon Valley, office in China as well. We've developed over 400 products. So a long history, lots of different industries, and really we're providing that engineering analysis and the manufacturing considerations kind of in that design frame. A little background on kind of who we work with. Interestingly, we actually design robots, and we also design products. And we design robots that are products in some cases. Robotics, Boston Dynamics, Google, Teradyne, their robotics platforms, work with Google robots, work with Universal robots, kind of across the board. Also work in the kind of higher-end consumer space where it's really cost-driven, where robots are used to actually assemble those. A couple of little pictures of some robots we've done, some higher-end products, imaging systems, automation systems. So a little bit more about us. DFMA, it's a great buzzword these days. I think we take it as really kind of part of our DNA. That was really the historical piece of the company, or the historical background of the company was when Ken and Tim were both working for Next, they couldn't get outside consultants that could make something past the prototype. That how do I turn this into revenue? How do I get this into production? What are all those steps that I'm missing? I'll talk a little bit today about Boothroyd Dewhurst. Does anyone know what that is? Good? Got a couple engineers in the room, sounds like. It's good. That's a modeling approach for figuring out cost of assembly, cost of manufacture, touch time. How do I analyze a concept, analyze a product that'll tell me or predict what are my assembly costs going to be, or what's my assembly time going to be, and how do I apply that for different regions. It's a little different than the generic kind of label of DFMA. It's kind of a specific toolkit that we use. Also interesting perspective of kind of the design side perspective of design for manufacturing versus a contract manufacturing perspective. We have different goals in mind. Sometimes they're aligned, sometimes they're not. Contract manufacturers want to make the product as cheaply as they can, and that's good because they're gonna make money, and being profitable and their supply chain profitable is a key piece of this. But we also need to keep the performance, keep the reliability, keep the wants of the consumer in mind. And we kind of approach it as this is one of our toolkits that we use, but we don't really have a horse in the game in terms of you need to use this particular platform, you need to use this contract manufacturer, you need to use this region. We're kind of applying this at a general scale. I stole some of Brad's slides for this, so I promised I would keep this picture in mind here. This is his newborn baby at the time. But we do try and take some baby steps as we go. So a lot of clients are not comfortable with a complete revolution in their process. So I think the earlier examples were great of, hey, let's add a robot to do this step. Let's add a piece to do this element. We're not trying to go to a lights out automation, 24/7 for every product. The other thing that we find surprising is clients don't always track cost. We're always surprised by that. And we try and keep that first and foremost. That is a key part of the business, is that you do have to be able to sell these products and everyone make money. Some great excuses we've heard. You can't estimate things accurately, certainly not early in the design phase. Oh, we do this already, it doesn't cost anything. My favorite is the CM will figure this out. If there's any contract manufacturers in the room, you know exactly what we're talking about. And that is not always the cheapest path. So, a couple of case studies we want to talk through today. And please jump in with questions and other comments and things as we go through. I'm happy to break as we go through this too. So, 3 different platforms. I tried to take a little snapshot of kind of manual assembly. The middle one is high value, relatively low volume assembly. And the last is a relatively low cost, very high volume assembly that we worked on. Kind of what were the problems and challenges as we go through these? How do we establish cost models? How do we do some predictive analysis based on these? Using this analysis, how do we compare solutions? What recommendations do we make? And then how do these change based on the scale of the system, the scale of the product? So first case study, this is an optical assembly, part of a kind of high-end projection system. This is a kind of a beam steerer per se, but there's a bunch of mechanisms inside. There's some optics. It's actively steering some projected light. Lots of little tiny parts. There's lots of these in the assembly. This is kind of a relatively low volume but very high-end kind of visual system. Only about 12,000 units a year, but there's lots of these inside the system. So in the individual part size, there's actually quite a few parts. We were brought in relatively early in the design process. They had a concept, they had a prototype that was working, and they realized it was going to be way too expensive. And we kind of stepped in and said, how can we improve this? How can we reduce the cost? So running through some of our analysis, and I'll try to skip some of the data and the lovely spreadsheets as we go. But this is 374 parts, which is a lot of parts. There's something called the DFA index. It's a little bit out of favor these days from a tracking metric. It's a method of overall assembly efficiency. So number of, did I get this right? Minimum theoretical parts over actual parts. So things like screws, things like brackets, things like spacers or other things that don't really do the function of the assembly but are there just to kind of put it together. Those are the overhead. And you'd like this to be as high as you can. Ranges in the 30% is really good, and 5% is kind of bad. The thing it doesn't do is it doesn't necessarily track the overall cost of the assembly or overall. You can have a relatively low index for a high expensive system. It's okay, but more detail on that later if anyone's interested. A lot of times in very few parts. again, kind of Paretoing this, saying where do we want to attack? What makes sense from an automation standpoint? What makes sense from a robotics standpoint? Largest contributor is obviously huge here in the chart. And we did this model kind of blind. Our customers like us to do that. We hate doing it because we always like to know the answer before we do the analysis, but we actually ran through it and actually came out about 8% off from what their actual takt time was on their current assembly process. So pretty good resolution on predictive modeling works with what they actually get. So it took them about an hour to do the overall assembly. So questions here, what do we automate if we do? What do we want to redesign? Do we just want to move this to a low-cost region? What impact does that have? What could we save? You know, again, what's our recommendation based on data? So we go through, this is kind of a summary table of some of the action items, and I won't go into lots of detail on them, but obviously snaps, better alignment, self-aligning parts, removal of hardware, single-axis assembly, you know, all of those checklist items will kind of implement as we go through. And we can kind of tabulate out a bunch of these different solutions here on what do we think is the right mix. Each of them have a different ROI aspect to them. Do we need to change fixturing? Do we need to retool parts? Is there capital involved or not? And what do we think our assembly time can be reduced to? In this case, you know, the client ended up picking kind of their top line items based on their ROI expectations, and they ended up keeping it all manual assembly. So we reduced it by about half, I think. It was 0.9 to about 0.4 total assembly time. Lots of challenges here as we go through. High tolerance parts, optics, thermal sensitivities, lots of harsh environments. These are all kind of stacked considerations as we go to redesign elements. We'll talk a little more about some tolerance concerns as we go. And overall results, this is about $500,000 in savings to the client. It was 100% realized, so they actually went and implemented all of these solutions, and we actually went and helped them implement all of these. About a half, or more than half, reduction in parts, about a half reduction in cycle time. And those do tend to correlate pretty well. So, again, kind of a purely manual solution, just as a comparison. Second system, this is kind of a high-end test system, lots of parts, very high value, kind of the same volume range, but significantly more expensive. It took about 3 hours to put together, really labor intensive, and we were not allowed to change any of the tooled parts in this case. So again, an ROI restriction there on what we could change, what we couldn't. A little snapshot of going through some homemade Boothroyd models that we've done. For folks that are familiar with it, you know, it's a kind of a litany of steps as you go through. How is a part added? Is it secured by itself? You have to hold it in place. Does it self-align? Does it have lead-in? Is it keyed? A bunch of these steps as you go through, and you can figure out kind of what is your estimated assembly time based on all of those steps. You have to flip the part over. Is it blind? Is it a special tool? Is it a different tool than the last tool? Again, kind of a matrix here of these decisions as we go through. So we ran through this model. Again, made a similar Pareto chart based on the data. Very different results, I think, from the last time, a little more distributed. Certainly a couple of peaks in the beginning. Correlation. Anytime we make a model, we do like to do correlations as well. Overall, our predicted value and actual times were very, very close. The bigger assemblies we do, the better averaging we get kind of across assemblies, so we tend to be pretty close. Here, we ended up doing some less exciting automation solutions. We love the single-axis robot arms, or multi-axis single arms, but this is a kind of 2D glue system that we implemented. Again, kind of a trace, form, and place kind of gasket solution to do some of the epoxying steps. You know, again, from an ROI perspective, factoring in cost, assembly setup, changeover support, nests, fixtures, design change, all of those things kind of factor into the ROI model. Ended up making a bunch of dedicated assembly fixtures. So the definition of robot is pretty wide these days. So these are kind of semi-automated solutions. Again, from overall decisions from the client on what they want to implement. Total roll-ups here, again, pretty significant from an overall cost standpoint. We actually could have reduced the assembly time actually quite a bit more, but they prioritized ROI over overall assembly. So can't fault them for wanting to get their money out. And then the last case I want to talk through is kind of the other end of the spectrum. These are a couple of products. These are not the actual products. I can't find them anymore because they go out of date so fast that I can't find pictures of the real thing anymore. But these are cell phone optics, cell phone camera systems. We were doing these back in the 4, 6, 8 megapixel range, which is now like archaic from a camera standpoint. But really unique challenges. Probably the highest volume stuff we've worked on. These were ramping. The steady state run rate was 20 million units a month, which is an unbelievable number. Yeah. Just sourcing, logistics, everything else. So from the start, what level of automation do we need, particularly on the assembly and test side, was really key. The other challenge here is the design cycle for the optics and the sensors were about 9 months, and the product life was about 6 months. So we had 2 or 3 designs all in queue at the same time. We would get to the point where we'd release tooling, and they'd say, great, here's the next one. And while that's being tooled, you can design the next one. So lots of strange challenges there. Again, an interesting cost was kind of a distant third from the criteria here. As the parts shrink, the cost is more dependent on the technology than kind of what you do from an assembly standpoint. So, again, designed here from the start from a robotic solution. Because the product life cycle was so short, they were really hesitant to do any dedicated tooling. So a particular robotic line or a particular platform, they needed high changeover. They didn't mind using people. They called them human servos, which are a nice term for people. But people are very good at certain things, and they're not so great at other things. So in the design cycle here, we actually did the overall product design of the packaging, the lens system, and the autofocus system. It's no surprise that if you can see on those pictures up there, the divots and kind of tooling features you see on the end of the lens, those are very specific. That was a great amount of time in terms of figuring out what shape those should be. We actually designed the end of arm tooling on the robotics in parallel with the product. We had to have essentially a 0 insertion force on the end effector, provide a particular resolution on our theta to do our initial focus setting, and be out of the way of all the optics and kind of run the thing live while we're doing all that. So interesting parallel effort here of the automation system and the product really from day one. Obviously I had to follow a bunch of other high volume rules here. Single axis assembly was critical. We're still doing a glue in place or fix in place assembly as well. Direct integration of test points, optical integration, field of view checks, things like that were all embedded in the design process. Talk a little bit about tolerancing here on the high volume products. This was really critical. Again, on the robotic side, do we have enough lead-in? Where does the compliance come from? How much do we need? How repeatable would this be? The difference between being 99.9% successful and 99.999% successful is a huge deal in that kind of volumes. Talk a little bit about kind of our approach for that. Tolerance on the focal plane. You know, how far do you have to thread the thing in to get it in focus? And how close can we get there? And how fast can we do it? And how close can we preset the distance to be, when we go to our final stage, the robot only has to go plus or minus 30 degrees or plus or minus 50 degrees in order to keep our throughput up. And then what's available, what do we need to bake into the parts from a tolerance perspective versus what can we do from an automation or assembly solution? Can we leave these as crude parts knowing that we can tune them all when we put them together, or do we need to bake the cost into the actual part? We have a pretty distinct tolerance control process for this. We try and absorb as much data we can from the actual manufacturer of the parts. So if there's some statisticians in the room, CPK or process capability, what does your normalized data look like of your particular part? How close are you to center? What's the peak of that curve? Input that data into our model and kind of get a predictive response. So we can add up a bunch of these elements add a bunch of different shaped curves to kind of get a composite curve of our outcome. And then from that, figure out statistically where do we expect to be. And applying that at that scale was really key because, again, from a statistician standpoint, you know, a 4 sigma design, 5 sigma design, 6 sigma design, they're all very distinct criteria as we go forward. Little snapshot here. This is kind of one of the dedicated fixtures we're using for the autofocus. There's some glue systems there as well. They ended up making about 80 the first generation, about 100 the next few generations of these automation platforms. They preferred the semi-automatic solutions and a person standing in front of them running them all. So we actually had a contract manufacturer making our automation systems and a manufacturer actually using the automation in their factory to make the products. So we had a pretty long supply chain from that standpoint. But we're able to meet all the ramp requirements as we went. So a couple conclusions here. You know, really no one size fits all. That's kind of our approach. We like data, we like numbers, we want to make a good decision based on the data. What's the right ROI? The CM and supply chain integration, kind of as early as possible, that's key. What capabilities do they have? What do we need to build? What toolkit do they have? What's their comfort factor in a particular process? Do we need to bring in additional skills or additional equipment? Defining our goals. We see this a lot from clients. What does my cost target really need to be viable? What are my volume limits that I'm setting? What's my ROI or capital budget? How do I define all my inputs to the problem? And then certainly knowing your numbers. You know, we like to provide data, recommend a decision, and kind of agree on what we think the best path forward is. And early and often, it's a great motto, but also better late than never. We certainly see that as well. We get brought in towards the end of some solutions of, can't you make this cheaper? Questions, comments, thoughts? A little different perspective on the input side here to the process. I wish I had more robot pictures to show. All right, thank you.